This is physicist Richard Feynman. He argued that if all scientific knowledge were about to be destroyed, the single most valuable sentence to pass on to the next generation would be the atomic hypothesis, the idea that all things are made of tiny particles in perpetual motion. That specific hypothesis traces back to the early 19th century. John Dalton proposed the atomic theory to explain why chemical elements always combine in fixed proportions by mass. Decades later, James Clerk Maxwell and others took Dalton's concept even further. They developed kinetic theory, treating gases not as continuous static fluids, but as vast collections of rapidly moving particles. Ludwig Boltzmann then provided the rigorous mathematics to back this theory up, proving that the macroscopic temperature we feel is actually a measure of the average kinetic energy of these microscopic collisions. We no longer have to rely solely on their math. This image from a scanning tunneling microscope captures individual atoms arranged in a ring, physically confirming the structure of the atomic world. In solids and liquids, atoms are packed tightly together, but in a gas, the interatomic forces are negligible. The molecules are free to travel in straight lines, obeying Newton's first law of motion. Because they are completely free of attractive forces, their velocity is extreme. At room temperature, the root mean square speed of a single nitrogen molecule is 516 meters per second. That means the seemingly still, quiet air in any room you sit in is actually a storm of particles moving faster than the speed of sound. This creates an immediate, striking physical paradox. If the molecules are moving at over 500 meters per second, a scent released on one side of a room should reach you almost instantly. Instead, it takes minutes. The delay happens because the molecule does not have a clear runway. The space it moves through is densely packed. Its journey is constantly interrupted, crashing and rebounding in an entirely new direction through elastic collisions. That single straight line between two impacts is the mean free path, denoted by L. This short distance is the true bottleneck of molecular motion. To accurately predict how gases behave, we have to calculate the exact distance a molecule can travel before it inevitably crashes. We can derive this mathematically. A molecule with diameter d moving at speed v over time delta t sweeps out a cylinder. Multiplying this swept volume by the number density n yields the total collisions, isolating tau, the time between impacts. We now have a mathematical expression for the time between crashes. This gives us the final variable needed to calculate the distance. The mean free path, L, is simply the molecule's speed multiplied by the time between crashes, tau. When we substitute our equation, the speed variable cancels out entirely. But this specific result relies on a physical impossibility. Target molecules are not frozen. In a real gas, every particle moves chaotically at hypersonic speeds. When objects are in motion, they close the distance faster than if one is stationary. The calculation requires using their relative velocity. Accounting for relative velocity across randomized trajectories introduces a correction factor, the square root of 2, into our equation's denominator. In this final equation, the distance between collisions is dictated purely by the physical size of the molecules and their density. Their speed does not matter. To see exactly how density controls that distance, we can look at the physical expansion of water into steam. In liquid water, mass density is 1,000 kilograms per cubic meter, with an interatomic distance of 2 angstroms. When boiling into vapor, density drops to 0.6, occupying 1,600 times more volume. The mean free path extends to thousands of angstroms. This vast, empty runway between collisions, often 1,500 times longer than the molecule itself, is the architectural difference between an incompressible liquid and a highly compressible gas. Because kinetic energy is tied directly to temperature, all molecules in a gas at the same temperature share the same average kinetic energy. That means lighter molecules inherently travel at a greater root mean square speed than heavier ones. We can physically exploit this slight difference in speed and collision rates to separate isotopes. In the nuclear industry, a mixture of uranium-235 and 238 is converted into a gas and pumped into a porous cylinder. Uranium-235 is slightly lighter. It moves faster, hits the porous walls of the cylinder more often, and leaks through the barriers at a slightly higher rate. slowly enriching the mixture on the other side. The difference in mass is so incredibly small that separating a useful amount requires repeating this diffusion process thousands of times, necessitating the immense industrial footprint seen in this photograph. Every macroscopic property of a gas we observe, from the time it takes a scent to cross a room to the industrial separation of nuclear fuel, is the direct result of a continuous microscopic pinball game constrained entirely by the geometry of the mean free path.